Good morning and welcome again to the Communication Signal Processing Seminar. Today is the last of our experiments. I guess we do have this semester. We had speakers from outside the U.S. and it's my. So before I introduce the speaker, I should thank Shelley Feldkamp and Catherine Gordon, who have been the people behind the scenes, making sure that everything, even the meetings, the talk, timing, everything is organized well. So yes, it's my great pleasure that we could have Vivek Borkar be a seminar speaker. I've been asking him to come and give a talk for a very long time, but this seems to be the best occasion to do it. Vivek obtained his BTech in electrical engineering from the Indian Institute of Technology, Bombay, and a master's in systems and control from Case Western Reserve University, and then a Ph.D. in electrical engineering computer science from the University of California, Berkeley. These are all 1976, 1977, and 1980 respectively. So he's held after that he's held lots of positions in various institutes in India, including TIFR Center for Applicable Mathematics, the Indian Institute of Science in Bangalore, the TIFR Center in Mumbai, and then the IIT Mumbai. Since July 2020, he's an emeritus fellow at the IIT Mumbai with the S.S. Bhatnagar Fellowship from the Council of Scientific and Industrial Research, the Government of India. He has won several awards. He's a fellow of the IEEE, the AMS, TWAS, and various science and engineering academies in India. He's also won several awards in India, was an invited speaker at the International Congress of Mathematics in 2006. He's written several books, including a very popular book on stochastic approximation. He has developed, in terms of his achievements, I mean, there's a lot of foundational work in stochastic control, in adaptive control, in reinforcement learning, in stochastic approximation. We have Zoom bombing going on right now. And in general, so his research interests are in the broad domain of stochastic optimization and control, spanning theory, algorithms, and applications. I have for me, it's a personal pleasure to have Vivek speak. I remember taking one of my first serious probability classes with him when I was a student at the Indian Institute of Science in Bangalore. And he was also, at that time we also had a qualifier and it was on the board in person. And then Vivek was very gentle with me, so I still remember that. He could have asked me the toughest questions, but he actually held my hand through. And ever since that interaction, he's always he's kept an eye out for me. So I consider him one of my mentors, and it's my pleasure to have him speak. So with this, I will give the floor to Vivek.
Thanks, Vijay, for the introduction. So, okay, so you know the title of my talk anyway, but the outline. Okay. Yes, the outline is as follows. I'll give assume that people who are attending the talk have varied backgrounds. There's some kind of background material I'll cover. For some of you, it may be standard, already known. So please bear with me. So the first bullet is like that. So I'll just very briefly mention the ODE or Ordinary Differential Equation approach to stochastic approximation. Then also very briefly introduce Q-learning algorithm of Watkins. The reason I'm introducing this, which is anyway well known, is because I want to show I want to project it as a stochastic approximation. So exactly for a stochastic approximation person, how it looks. Then the main theme, which is the prospect theoretic Q-learning, which is joint work with undergraduate student in IIT Bombay now in his final year, Siddharth Chanda. Now, if there's time, this I may not get to, but if there's time, there's some work I'm currently doing with a variant of DQN, which are another undergraduate student, Harsh Dolare, and team from Indriya Sofia Antipolis, that's Konstantin Avrachenkov, and his postdoc, Kishore Patil. So this I may or may not talk about. So let's start. So this is stochastic approximation. As I said, I'm presenting a particular perspective, namely the noisy discretization of an ordinary differential equation. So the origin of this algorithm is the problem of solving finding roots of a nonlinear function given its noisy measurements. So the idea was that there's some black box, you feed in some x and out comes hx plus noise. Okay, so and the Robinson Monroe go with this.
Vivek,
Yeah.
One quick thing. There is some echo coming, but I don't know if that's just how it is.
Oh, I'm using a headphone, so maybe somebody
Okay.
not muted. Perhaps I don't know. Whether that's the reason.
Yeah, maybe. Let me double check. Let me mute. Oops, 1 second. Let me just quickly check. No, everyone seems to be muted except me, but I'll come. All right, please go ahead. Yeah.
Okay, yeah. So what I was saying was that the origins of the problem is in solving the nonlinear finding roots of a nonlinear function given noisy measurements. So you imagine a black box in which given x spits out hx plus some noise, and Robbins and Monroe came up with this clever algorithm. We simply start with some initial guess and iterate xn plus 1 is xn plus n times h of xn plus mn plus 1. And the important point is that the square bracket is the measurement. So you do not know hxn and mn plus 1 separately. Mn plus 1 is the noise, and but all you see is the sum. Okay, and n is the step size or learning parameter, and the sort of very clever thing they came up with was this condition: sum of n is infinite, but sum of this should be small, and sum of n square should be finite. So it's a slowly decreasing sequence. So there are some examples, but this makes eminent sense once you think of it as a different approximation to differential equation, although they did not think of it that way. So it was quite ingenious of them to come up with this. Okay, let me first go through some standard technical assumptions. This is a convenient level of generality. You can relax them for specific problems. So one generally assumes that Hx is Lipschitz, and if Fn is the sigma field of, so Mn is the square integrable martingale difference sequence. Okay. So in the sense that by square integrable, I just mean this second movement is bounded, and martingale difference in the sense that the conditional expectation given everything up to the previous time instant is 0. So Fn is the sigma field of all random variables realized till time n, and conditional expectation component wise. So I m sub I is ith component given Fn is 0 for all I. So in particular, what it means is that it's uncorrelated with the past. So take any function of all these random variables x0 and all the m sub m of n realized up to time n, then mi n plus 1 will be uncorrelated with that. Okay. And in addition, this is a technical condition, some kind of conditional second movement satisfies this growth condition. So it's bounded by some constant plus constant is 1 plus square of the current iterate. Okay, now this differential equation, these are the papers I used to refer to, but today I came to know that Professor Mirkov had also contributed to this one before. These people did. So I'll correct my slides in future. So this was a paper from, I think, St. Petersburg in 74, and then Leonard Leung published in IEEE Automatic Controller in 1977. Sort of developing this approach further. And the idea is simple. So you treat it as a noisy discretization of the differential equation. So think of if there was no noise and if n was constant, it would just be the Euler scheme. Okay? The usual discretization scheme, simplest discretization scheme for the differential equation. So what you have here is a discretization with slowly decreasing step sizes and in addition measurement noise. Okay? And the claim is that under reasonable conditions, which I technically I won't get into, the iterates track the asymptotic behavior of the ODE. And you can think of it as the you can sort of, one way to think of it is the stochastic approximation averages out the noise. Okay, in fact, the strong law of large numbers can be sort of cast as a stochastic approximation, though that would be a hard way of doing it. But you can think of it as some kind of averaging and some kind of a extension of strong law of large numbers to certain kind of dependent variables. Okay. So let me just go back here to the step sizes. And what I'm going to, as I said, I'm thinking of n as a time step. So this, what sum of n is equal to infinity says that you are covering the entire time axis. And that's important because you want to capture the asymptotic behavior of the ODE. Okay, you don't want to simulate ODE on a finite time interval. You want to capture its asymptotic behavior. So that's what this condition does. This condition implies n going to 0, which in particular implies there are two kinds of errors. There's a discretization error that goes to 0 if n goes to 0. So that's good enough. But what we have is something stronger, and that essentially, coupled with other conditions I have put, ensures that error due to noise also asymptotically goes to 0, and that's how it starts tracking the differential equation. That's the rough idea of the proof, basically. So let me go to Q-learning. Okay, and again, as I said, I want to cast Q-learning as a stochastic approximation algorithm, and this was one of the classical reinforcement learning algorithms introduced by this gentleman, Christopher John Watkins. This was part of his Ph.D. thesis called Learning from Delayed Rewards in King's College, Cambridge. And in Wikipedia says that there was something very close preceding it by Bozinovsky, and gives a reference to a couple of papers which are in some conferences which I could not locate. So I'm just quoting Wikipedia here. The first convergence proof was also given by Watkins and Dayan. There are subsequent convergence proofs by others. This one by Sisiklis, one by Yakola, Singh, and Jordan, and so on. So in fact, I will give some ODE proof here. So this is the gentleman. He is now in Royal Holloway College, London. Professor Watkins. Okay, so let me quickly introduce the framework, which again many of you probably know. So I'll probably go through it somewhat fast. So we look at a controlled Markov chain Xn on a finite state space and controlled by a control sequence Un, which takes values in also in a finite action space A. And the transition kernel I write at Pj given I, which is a controlled transition kernel, which is basically specifies the probability of going from I to J under control choice U. And this is a controlled Markov probability that Xn plus J given the entire partial n depends only on Xn and Un, current state and current control. And there are some special classes of control policies we use, and one particular, and this is the most important, if you take Un to be the a function of the current state, it's called a stationary policy. And usually one simply identifies it with this map U from the state space to action space. This is also stationary randomized policy, which is used in some reinforcement learning often, and that chooses control randomly, but that randomization is conditionally independent of everything else given the current state. So probability that Un equal to U given the entire the past and the current state and the past actions depends only on the current state. So this is some probability distribution phi, and again one identifies the policy with the map phi, which will now go from the state space to, sorry, this should have been A here, to probability measure on action space. Okay, and then I'll look at the infinite horizon discounted reward, and this is sort of the simplest case to analyze. There are extensions to other more complicated things also, where K is some kind of running cost. We assume takes values in some bounded interval K min and K max, which without loss of generality I can take to be strictly positive, strictly positive real axis. And the value or the maximum reward to go from state I is the max over this for all admissible controls. And one knows that it satisfies the dynamic programming equation given here, the Bellman equation. What's more, one knows that if you maximize this over U, so the maximizer will depend on I, need not be unique, but suppose you pick one for each I, So V sub I, which is the maximizer here, gives you an optimal stationary power policy. So if you choose UN to be all n, that will be optimal. So all this is classical background. And furthermore, there's this value iteration. So basically, if you know V, you know what you have a recipe for finding the optimal stationary policy. So you have to find V, and this is one of the standard algorithms called value iteration. You simply keep iterating, start with some initial guess V0 and keep iterating. And one can show that it will converge exponentially to the correct solution, because essentially that the dynamic programming equation, which is of the form V equal to some f of V, that f is a contraction map. So it's a very clean convergence argument. Now the point is, when P is either unknown or very complicated, then you want some data-driven scheme to compute V. Okay. So here I'm assuming that you know V, and also you can compute conditional expectation, etc. very easily. So that may not be the case if it's a very large problem and so on. So let me start with a very naive thing one could dream of. So instead of computing this, computing the conditional expectation, simply plug in some real or simulated random variable, which are called psi sub iu of n, with law given by the transition probability P of dot given I comma u. Okay, so I replace this sum over j of P j given iu Vn j simply by Vn of psi sub iu n, okay, and hope that it works. But then that won't work. So what you have to do is basically exploit the averaging property of stochastic approximation. That's why I emphasize the fact that what stochastic approximation does is some kind of averaging out of the noise. Now, if you try to do that, you run into trouble already, because you want that conditional average. I mean, I'm saying averaging, but what it actually is a conditional average here. And there's a max sitting outside. So stochastic approximation will put the averaging on the outside. So you get average of max instead of max of average. Okay, you have to interchange the two. So one thing Q-learning does, so of course there's a stochastic approximation viewpoint of why Q-learning, is to interchange the max and the average. So I define Q value as simply the quantity which was in the square brackets in the dynamic programming equation, this quantity which is minimized over U. Then certainly V of I by dynamic programming equation, V of I is simply max over A of Qi comma A. And then Q, if I plug this V, replace V by this expression, I have this kind of dynamic programming equation for the Q values. The equation at the top, and then I can write a iterative scheme for that as well, which is here. And then do what I just suggested. Plug in, get rid of the conditional expression, plug in the random variable psi iu n with the correct conditional law, and take a convex combination with the previous iterate, which is Qn, and a new correction term, which is whatever you are plugging in gave you. So with weight 1 minus an on the previous iterate and an on the new information. So it's kind of, I'm just making it incremental. So that's what the Q-learning, synchronous version of the Q-learning algorithm is. So if I rearrange terms, it looks like this. I just put together everything that multiplies A of n. So I have taken this minus a n q n I comma u on the right hand side, and this is a synchronous Q-learning algorithm. So these are the n satisfies the Robins-Monroe conditions, and psi iu n are independent as well as random variables with the respective laws given by the correct transition probability. But what one usually does is have a single run, just simulate one controlled Markov chain. And then when the chain is in state I and you use control U, then xn plus 1 has the correct conditional law, okay, which is what you want. So you update the I comma youth component and you leave alone the rest. So this is the real Q-learning algorithm. So this is an indicator of xn equal to I of xn equal to I, un equal to u is just indicator function, which is 1 if xn is I and un is u, 0 otherwise. So I comma youth component gets updated and the others remain unchanged. And I want to introduce this term new I comma u comma n, which is just the some partial sums of these indicators from 0 to n. You can think of it as a local clock at I, u. And this, I'm calling it local clock because this is a general terminology which carries over to more generally to distributed algorithms. Here, of course, you may be running just a single processor running the simulation. But nevertheless, let me call this local clock at I, u. And I'll assume this condition holds that this is the relative frequency with which I, u was updated, and I want it bounded away from 0 almost surely. What it means is that you are assuming you are doing comparable exploration. You are updating every component comparably often. And that's important. This is definitely a sufficient condition. Sometimes you can work around it also, but certainly a sufficient condition for many algorithms to converge to show desirable convergence. So now the dynamic programming equation, as I already mentioned, is of the form I had mentioned it for Q for B, but even for Q, it's of the form P equal to FQ. The fixed point equation where the F is a maximum contraction, so it has a unique fixed point Q star, which is what we are looking for. And then the ODE tells you that the stochastic approximation, the synchronous case will track this ODE, Q dot T equal to FQT minus QT. Okay. Then one can show that actually this the maximum distance from the Q star, the fixed point, actually serves as a Lyapunov function. Now this is not differentiable, but what you can show is that the maximum of Qt minus Q star monotonically decreases along the trajectory. There's some, because it's not differentiable, you first work with some p less than infinity and then write it as an integral equation and let p go to infinity. Some approximation argument involved, but it works and it will monotonically decrease. So it does serve as a Lyapunov function, and you can show that it converges to Q star. And then by the standard stochastic approximation, the tracking property which I mentioned, Qn goes to Q star with probability 1. Now asynchronous case gets a little more complicated. It gets the ODE gets this time varying diagonal matrix upfront. So I can cast it into the original form by replacing f by f sub t, where f sub t is just by adding and subtracting terms, you reduce it to this. And here what happens is that this lambda t happens to be a diagonal matrix where the diagonal terms reflect the relative frequencies, actually the non-negative relative frequencies with which the corresponding component got updated. And actually here I can mimic that argument. See the ft, okay, all this time dependent, they have a common contraction factor. They're all contraction map. They have the common fixed point and common contraction factor. So you can just push the same argument through and get this get the same. The contraction factor reduces a bit, but you get the same argument. So what I'm going to do when I talk about the prospect theoretic learning is not get into these technicalities, because the idea there was to basically get a qualitative feel for what happens. This will only introduce a lot more notational complications. So we have not done that. So what essentially I will be analyzing this ODE. Q dot T is FQT minus QT. Not exactly this, rig the algorithm a bit, that you will see soon. Of course, prospect theory demands that you sort of introduce a nonlinearity, which we did, but in addition to that, we also introduced some extra noise. I'll come to that later. Okay, so this is just to mention that in principle, one could have done the same thing with for the more general case, as long as all components are updated frequently, but it would be just some additional bookkeeping and notational overhead to contend with. So this is, now I come to my main theme, which is prospect theoretic Q-learning, and this I am going to basically analyze as monotone dynamics. So prospect theory and cumulative prospect theory due to Kahneman and Tversky. Recently, the first paper is by Kahneman and Tversky, and the second paper is by Tversky and Kahneman. And recently attended a talk by Robert Aumann, who found that fact very amusing. Anyway, it is the same two people, just different order. And what it does is it's basically part of the behavioral economics. It factors in peculiarities of human judgment, namely humans downplay increasing rewards and both rewards and losses are underplayed by our judgment. So in other words, they're seen through the length of an S-shaped curve. So you apply some S-shaped nonlinearity. I have a figure here. So you sort of, there's some nominal reference point. Above that, you tend to sort of use a function like this, which will downplay the high values for the rewards. And similarly, on the other side, you'll have this convex like function, and that will downplay the losses. So that's the idea. So I'll define this A, B, C, D, etc. later. You'll see this figure again and again. And so we take Q-learning as a model. So here I'm not treating as a reinforcement learning algorithm per se, but as a human decision model for human decision making and cause future returns to an S-shaped continuously differential function group. And there was a nice PhD thesis by Yun Shen in the Technical University of Munich, where he first analyzed this thing, and he considers a few variants, and it also has some analysis of fMRI data, and shows that it matches one of his models. It's quite a nice thesis. Of course, this published version of the work, also the paper which described this data analysis, appeared in Neural Computation. Okay, so this was a figure, and the objective is to, of course, to study this. And if alpha is, in case of alpha sufficiently small, okay, then even after you apply this U, if I take alpha sufficiently small, the whole thing, the contraction property remains, and therefore the similar argument works. And this is one of the cases covered by it. The other case actually changes the algorithm in a completely different manner that I won't get into, but this is the kind of easy case. Just assume the discount factor is small enough so that things work. But we want to get rid of that assumption, so that was the main objective. And okay, maybe I should also add that although I have said that kind of just want, I'm treating this as a model, I also want to say that this can be relevant in various engineering problems where there are humans in the loop. So that you crowdsource some decisions to people, or whatever, auctions and so on. So once you have humans in the loop, you have to allow for human errors. And then this prospect theory is empirically validated model. It's not purely academic. This empirical evidence which the creators of the subject and others provided that people do think along those lines. So it's a legitimate model which one might want to sort of factor into any algorithm which has humans in the loop.
So Vivek, I had a quick question here.
Yeah.
So in some sense, this prospect theory basically it just models how humans may treat risk, but you could consider this in the general risk sensitive way as well, where you don't have the S-shaped function, but maybe some sort of concave, depending on if you're risk averse or risk neutral. I mean,
yeah, actually, concave convex can be would become a special case of this, because see, okay, maybe I'll go back to the figure. See, the figure doesn't have to look. I took an S-shaped curve, but some of these regions, so I'll identify various regions. So see, if alpha, if the slope up to this point the slope is strictly less than 1 by alpha, there could be a patch where it's equal to 1 by alpha. So this U prime is basically it's flat there, and so this is less than 1 by alpha, this is equal to 1 by alpha, strictly greater than 1 by alpha, again equal to 1 by alpha, and again less than 1 by alpha. Now, any of these regions can shrink. So, if this point, if I move to the left, it will become convex. If I move to the right, it will become concave. Sorry, the other way. If I move it to the left, it will become concave, and the other way will become convex. So, that's subsumed here. But there's, of course, there's a lot of work on this CVAR and that kind of risk measures. I have not thought about how this would map there. That might be interesting to see. There's a lot of reinforcement learning algorithms developed for the risk measures coming up in finance. Most recently, I've seen a paper by Brzezinski in Rutgers and Borkar. Does that answer your question?
yes, yeah, thank you. Yeah.
Okay, so I have here what I have plugged in. So where you put U is a kind of it's no unique choice. I'll talk about another choice later. but we have put it around, because I don't think the qualitatively the matter don't change. We have put it around basically the whatever involves the future, which is UXN plus UN plus 1. I will describe how where UN plus 1 comes from. And I have also put this noise, which is talk about. So I assume that this you see future in a noisy manner, which so of course, so in addition to giving us somewhat extra reality touch, it enormously simplifies the mathematics. So there's some kind of self-interest involved here. I will soon talk about that as well. So, okay, so right now I'm anyway, as I said, I'll look at the ODE. So going back, I'll just use the okay. Oh, sorry, I've actually written the asynchronous thing here and then gone on to talk about the synchronous case here. Looks like okay. Yeah. So anyway, so the UN plus 1 is one of the standard things people do is the epsilon greedy policy. So the algorithm would have a max over the control there. So what you do is that you take the max of the current, the maximizer of the current value. So maximize Qn of xn plus 1 comma a over a, and take that value with probability 1 minus epsilon, and then randomize uniformly with probability epsilon. This is a standard thing, and the reason is clearly, if you go totally greedy, namely you just take UN plus 1 equal to the maximizer, then the problem of insufficient exploration comes up. So I had assumed that I had this comparable exploration for all components, namely the relative frequency with which each component gets updated is bounded away from 0. You can't ensure that if you do this. You can get trapped into some wrong decision quickly. So that's why this is one of the standard things people do. And of course, there are variants such as you decrease epsilon very slowly and so on, but I'll stick to that, stick to this. So I'm assuming the standard epsilon greedy policy. You take the maximizer, which is your current case. So Qn is your current case for Q star. So its maximizer will be your current case for the optimal decision. You use that with probability 1 minus epsilon, and with epsilon you randomize among the rest. Okay. And of course, this is another technical complication I won't get into. Namely, the maximizer may not be unique, and you just use some t-space divided to break the ties. Now, if I define capital K like this, you can, and I assume that U is the function S-shaped function that maps this set to this set. Okay, and then one can show that you start iteration in this particular product set, you will remain in it. Okay, and you can say the same thing for the ODE trajectory. Actually, take the discrete caricature of the discretization of the ODE, and you can show do the same basically by induction, and then pass through the limit and get the same thing. So one of the standard issues in stochastic approximation that you have to prove stability of your iterations, that's a non-issue here. They are bounded anyway, and that's because you are just taking convex combinations of your previous iterate and something else which is uniformly bounded. So you never get into stability issues. So this is something nice. Otherwise, the ODE analysis is conditioned on the iterates being bounded, and then that you have to prove separately. Now, this is the key definition. This ODE I call cooperative due to Morris Hirsch. If this cross derivatives, j not equal to I, are non-negative, and if you consider the elements of the Jacobian where they're strictly positive, then it should lead to an irreducible matrix in the Markov chains in the usual sense. I mean, if this is strictly positive, the ij term is strictly positive, you draw an arrow from I to j, and then there should be a path from any I to any j. Okay. So then you say that it's cooperative. And of course, this, if you reverse the inequality, it's called competitive, and that's much harder actually. There are not that many nice results there. And the limiting ODE turns out to be, okay, this turns out to be cooperative basically. The limiting, okay, sorry, let me first write down the limiting ODE, which is this. And what you see here is that this psi, okay, the noise, now this is just a variable that gets averaged out over the, so this it's a random variable which I have averaged out. Okay, I take the expectation. So as I said that I was kind of doing this for mathematical convenience, and the reason is that this expectation is just a convolution with respect to, so I assume that psi has a compactly supported smooth density or a continuously differentiable density, that's good enough. And then this is a convolution, and convolution makes the whole thing continuously differentiable. And one problem is that, the reason I am doing this is that a monotone dynamical systems theory requires continuous differentiability of the vector field. There's nothing available under only Lipschitz conditions. And this I cross-checked with Professor Harsh. Sent him an email and he confirmed that no such extension seems to be known. So we simply decided to, instead of fighting it out with Lipschitz, we decided to take the easy way out. We add this small noise, and basically it's just the smoothing of the right-hand side. Now that done, then one can check. I mean, just I have not written down the expression. It's a messy expression, but anyway, it turns out to be the cross derivatives are non-negative, etc. It's a cooperative order. Okay. And then one can simply invoke precious results. And one of the key things here is that it's a monotone system in the sense that, so of course, it's in d-dimensional space, so the inequality is a partial order. So if Q0 component wise dominates Q prime 0, then the trajectory continues, Qt continues to dominate Q prime T. Okay. Now, and the most important result is for initial conditions in an open, so assuming that the trajectories remain bounded, then for initial conditions in an open dense set, that means for generic initial conditions, the trajectories converge to the set of equilibria. There are some additional conditions under which you can say claim point convergence. So in the sense, if the set of equilibria is a continuum, then it may sort of wander around it, but never, in any case, it converges to the set of equilibria. So this is the major result. This is one of the few results where kind of non-standard convergence results, and it has algorithmic uses. Many people, including me, have used it for analyzing algorithms. One of the early ones I know, I think it's Whiting and Kushner, but there could be others. And this is another result. There will exist a maximal and minimal equilibrium. This actually they prove for discrete monotone systems, but you can take with the time one map of the ODE and invoke that result. There's a maximal and minimal equilibria, and now that we know that the ODE is converging to equilibria, anyway, any other equilibrium will lie in between the two. For actually discrete monotone systems, they need not converge to equilibria. So what it says is that there's a maximal and minimal equilibrium, and any other omega limit set will sit between the two. But this is continuous time, so we will have a stronger claim. So this inequalities are component wise. And there's this interesting result which we use, which is namely that one of the three must be true. There is a third equilibrium in between, or there's a trajectory such that it sort of goes from Q sub star to Q sub star. So at t goes to minus infinity, so the Q sub star is its alpha limit point, and Q star is its omega limit point, and so on, and the other way around. So it goes from Q sub star to Q sub star. So there are the three possibilities. One of the three must be true. At least one. So one of our claims is that if both these are stable, then yeah.
Top games. Work. You do school math. Come on.
Sorry. If both these are stable, then there's at least one more stable equilibrium in between, and that's because I should go to this picture from Wikipedia. This, of course, is for linear system. So in nonlinear case, you can suppose this is the equilibrium, which is hyperbolic, and then these just lines get morphed into stable and unstable manifolds. So if you are exactly on the stable manifold, you will converge there, and of course on unstable manifold you diverge, but anywhere else also you diverge. You may come close but then move away. So barring a zero major and nowhere dense set, you just move away. Okay, so generically the trajectory diverge, and that's the fact I want we use here. That if they're stable, I should have perhaps said hyperbolic also, that's right. Then because you know that So you basically you use that to get a contradiction to the to this case, okay? Because if this is true, okay, then there's at least a non-trivial unstable manifold, in which case most trajectories would be moving away. But then you know that from the earlier result, you know that anything which is which component-wise dominate Q sub star has to convert to Q sub star. So something in the all initial conditions in the positive cone shifted to Q sub star, which are actually they have non-empty interior. They will have to convert to Q sub star, so you get a contradiction. So this is not hard to prove. And if Q sub star is hyperbolic, then they are stable. And yeah, basically, I just forgot I have written this out here. So this is the fact that for a hyperbolic equilibrium that is not stable, trajectory is initiated in an open dense subset in an open neighborhood of the equilibrium must eventually move away from it. Okay, and you get a contradiction to this using the fact that anything in the positive quadrant planted at Q sub star or negative quadrant planted at Q sub star has to converge to respectively Q sub star and Q sub star. And then just recall the Perron-Frogenes theorem that any non-negative matrix has a dominant eigenvalue lambda a, which is greater than or equal to the absolute value of any other eigenvalue. And the other result is this, that it's sandwiched between the minimum row sums and maximum row sums. So this is used to prove various sort of characterizations for equilibria. So you remember that U is a S-shaped function and U prime is small towards the typically, as I said, you can shift, you can sort of shrink some of these regions to empty sets also. But suppose it's actually S-shaped as shown, then there will be some region where U prime is less than 1 by alpha and less than 1 and so on. So all this and it can exceed in the middle range. Okay, so if it is really small, then the contraction probably continues to hold, and as I said, Shane has already used that. So we try to generalize that. So so A is the point on the left of which U prime is less than 1 by alpha. Between A and D it's 1 by alpha. Between D and E is strictly bigger than 1 by alpha. Between E and D it's again 1 by alpha. Then B onwards it's again less than 1 by alpha. So that's the picture. And these are the various conditions. So suppose, yes, so this is just the definition of what I always. Suppose you start the ODE in this set, okay, and if there's an equilibrium, it has at most one equilibrium point. If there is one, it has to be a stable equilibrium and the maximum and stable and maximal equilibrium if it exists. As I said, the region itself may be empty. So if the region is non-empty and if there is an equilibrium in that region, it will have to be stable and the maximal, and there's a symmetric statement for the lower end that came into A minus C, a similar statement holds. So this is one of our results about location and existence of equilibria. Okay, so we'll keep showing this again and again, but I guess by now we will remember. Similarly between D and E, so between D and E, it's strictly bigger than U prime is strictly bigger than 1 by alpha. So if there's an equilibrium point, it will have to be unstable. Okay, that's the other result. And then there's another sufficient condition as it defines this object U1, and if this satisfies, then there is a stable maximal equilibrium point in this region. And if you start the iteration in this region, then it will converge to this equilibrium point. There's a symmetric statement on the lower side. I mean, they're kind of, I just hope that you get a flavor of the kind of results we have. I'm just rattling them away, but they have a similar flavor. Basically, we talk about the maximal and minimal equilibria. So in certain regions, if if such an equilibrium exists, it will be stable and maximal or stable and minimal on the upper and lower regions. And similarly, this is a kind of sufficient condition you can easily test. And so a symmetric statement on the lower side. Okay, so which tells you that there will be an equilibrium, and you can compute it if you start in the region. Again, the same thing.
So I had a question along this. So in some sense, you needed that smoothing with the zeta random variable.
Yeah.
So I can consider So suppose I consider a sequence of distributions such that it's basically, I still have the support that you're looking at, but they converge to zero in some sense.
Yeah.
Can I say anything about the limit points? And
no,
because I
actually,
know
it should be possible, but I'll tell you what will happen. So we have to push this result to. I mean, okay, it may be possible in this hyperbolic case. That's my feeling, because if you take an approximating sequence, okay, then some of these claims of Hirsch may be translatable to the limiting equation, but you are looking at asymptotic behavior, okay? And generally, you get convergence on compact time if you have parameters of converging to ODE. You have convergence on compact sets, but not asymptotically. You get it asymptotically if you have some kind of a Lyapunov function, which kind of holds true. So it's, the limiting system should have a Lyapunov function, which and if it does, then everything else is a small perturbation of the Lyapunov system. So if you have a Lyapunov function, if you have a small perturbation, it will go to the neighborhood of the equilibria. And that result, it should be possible to use. So it will be possible in special cases, I think, such as say this. So this, if all equilibria are hyperbolic, then it's a special case of the Morse-Smale system. And there's results by I forget the first person who did it. I think Meyer, yeah, Meyer and Smale show that there's a Lyapunov kind of Lyapunov function whose equilibria will match those hyperbolic equilibrium points. So I think it's possible and worth doing, but we have not done it yet.
Okay, thank you.
Okay, so this is the, I look at, okay, I don't know if I still have the figure. So M1 is the basically the point where the slope is maximum, okay, so kind of point of inflection. And the claim is that, yeah, so that's where this, and so the equilibrium points are hyperbolic and use convex above that M1 and below, convex below the M1 and convex above M1. Then this exists at most one stable equilibrium point in this region and similar in the other region. This basically this is a strong result, but so that's yet another statement about the existence of equilibria. And of course, if they exist, then and there's at most one, so they exist, there will be minimal and maximal equilibrium points. So this corollary is. So this is the reference to the point of inflection. Now, empirically, we had some interesting observations. Of course, the first one doesn't surprise you in the sense that if the discount factor is very small, suddenly you have nice things happen. But even if you violate that condition a bit and the point of inflection is not too sharp, you continue to get only one equilibrium point, which is reasonable. But most of the time, we kept getting at most two equilibria, and the convergence, depending on where you start, would go to one or the other. Then one of the advantages of IIT Bombay is that you are very smart undergrads, and Siddharth Chanda cooked up handcrafted examples where a third equilibrium exists. And then what we observed is that convergence to this third equilibrium is not very common, which means that the domain of attraction must be very small. Now, this is purely empirical. I don't know where there's something deeper hidden here, but this is what we observed. There's another thing perhaps worth chasing. So there can be, I guess, there can be more than three also, but the thing is that they tend to have, they usually miss them if you start somewhere at random, particularly if you start low or start high. So if you start low, typically you will go to a lower stable equilibrium. If you start high, you will go to a high stable equilibrium. But in between, you have to be really close by to one of these to get trapped. Then we tried, as I said, that you can argue why put you around this, you put you around that, and then you get, it's a theory is similar, but then some of these upper and lower regions tend to vanish. Well, okay, one more thing is that you can typically get bigger Q sub star and smaller Q sub star, and some of these regions tend to vanish. And then we have some sufficient conditions for them to not vanish. It's just It has the same flavor as whatever I said before, so I probably won't get into that. Okay, so I think I'll skip this, given that I think I was supposed to talk for 45 minutes and that time is already over. So maybe I can take questions now.
Sure. Yeah. So let me, if you can, yeah, so I'm going to share my screen briefly. So I'll just go through the quick thing and then we can use that as a thing to share, go for more questions. So I mean, I just have a few perspectives than anything else. So, so you can see my, yeah, so thank you again for a very nice talk. I mean, I enjoyed it. So let me give you just a high level overview in some sense, what you were, from the beginning, you were presenting a stochastic approximation based algorithm for solving Q-value fixed points in the reinforcement learning context. Is the rough highlight.
I think we cannot see your slide.
Oh, you cannot see my slide? Sorry. Maybe the thing.
I am unable to. I don't know what's happening. I can't locate. Okay.
Yeah. So now, yeah. Okay. Now.
I went to the wrong place. Okay.
Yeah. Yeah.
Now I can unshare. Okay. I will do that.
Yeah. No, I had to stop your screen sharing.
Yeah. Oh, you've already done that. Okay.
Yeah. Yeah. So the system asked me to do so.
Okay,
yeah. So then using the ODE method, you can sort of analyze the actual convergence properties of these stochastic approximation based algorithms. And this was illustrated, this method, for prospect theoretic RL, to put it finally. And there was a connection to monotone dynamic systems, which was the ODE that resulted in this. Okay. So this is just to give you a high level summary of what you presented. But I had a few thoughts and sort of questions were part of that. So most of first one is sort of on the rate of convergence in stochastic approximation scheme. So, so the ODE method that you presented, it relies usually on martingale convergence type ideas, and there's you discuss asymptotic limits, typically convergence to the ODE or differential equation to the equilibrium point of the ODE. So there has been some recent progress. I think Ley has been involved in that, using Stein's method and Lyapunov functions to track the error of the stochastic approximation estimate. Those seem to be the most commonly used ways to estimate the rate of convergence. Would you know of other methods to do so?
Traditionally, people basically see, if you assuming H is continuously differentiable, if you linearize around the iterates, you can prove functional central limit theorem, in particular central limit theorem as well for xn. Suppose you have a convergent stochastic approximation xn going to x star, the square root n times xn minus x star goes to Gaussian, and that is used as a kind of that's used basically as a convergence rate statement. For example, Sean Mine always uses them.
Okay.
So there are people use that. Then in terms of sample complexity, I have been doing some work which is, there are several different works. What I and my students have done is of a different variety than what others do. And there, particularly in the context of RL, there are recent work by this, I forget all the authors. I know Shivateja Magaluri is one of them, because he sent me the paper. Sanjay Jagota is another. There I think there's one or two more authors. Then there's also,
so I was going to come to that next. Basically, then the next thing in some sense is, how long do you run this thing for? I mean, you part of the thing of having a rate of convergence type thing, you know how many iterations to run the algorithm, how many random samples to pick up in various things. And that's usually this sample-based. And there seems to be two sort of competing ways of approaching that. The traditional viewpoint is this packed bound, which is probably approximately correct. So with some probability, the tail of the estimate is good. How many samples do you do? And then there's a recent work, flavor. I think initially it's related to what Shivateja and Sanjay's work, but it's sort of been pioneered more by Martin Wainwright, where he sort of says, hey, I have these, I can track the estimation error, usually a moment. This would be either the quadratic moment of the L infinity error, or the second moment, or the first moment itself. And then I say, if that is below epsilon, then I can say this is number of samples. the Folk theorem in some
sorry.
sense that these are equivalent up to log factors. And I've seen some proofs, but it's usually that you show that there's I mean, I have also done this where now you take the Lyapunov and you come up with a sample complexity bound, say this is what it is, and then say that, hey, you analyze for the same algorithm, a packed bound using different methods, and then say that they are equivalent up to log factors. But there doesn't seem to be sort of a common nice way to say, okay, if you do the work in one, you can just automatically get the other error. They are essentially the same. And it seems like the Lyapunov methods are easier to work with than the packed bound. Along the same thing.
Sorry. Yeah, continue.
Yeah, no. Yeah, so along the same thing, I was just going to add one more thing. So the packed bound community has minimax bounds, and seems that to attain these, you need to use some sort of variance reduction methods that could include in phases. And this seems to be the case for sample complexity. It seems like the Lyapunov methods, they end up using control variates. Again, there seems to be a lot of different methods, but there isn't a unifying theory. And so I'm wondering if you had any comments on that or on these differences.
Okay, so the recent works which I am aware of, one is, of course, as I said, Shivteja Maglori et al. Then there's again by Adam Wehrman and his students. And there are sort of sample complexity in the sense that they say at certain time n, what can we say? So the Shivateja, and there's yet another by Gyakanis and his student, and another one I recently saw by Daniel Russo and his students. I think most of them look at mean square error, but Wehrman has almost sure.
Yeah, Wehrman is the only one who's able to come up with a packed bound. Yeah.
Yeah, pathwise. Yeah. So what I have been doing is something different, which is basically getting bounds on from some time. So I take some n0 large enough, and that's primarily because I need n to have become small enough. Okay, have become small enough. So I get a high probability bound that for all n greater than or equal to n0, the iterates will remain within an epsilon tube of the ODE. So if the ODE is converging anyway, they will remain within epsilon of tube of the trajectory for all time, for all n greater than or equal to n0. It's an all-time bound with high probability. So the strength is that it's an all-time bound, but the weakness is that it's from some n0 onwards. So in some cases, I can kind of patch up this with the finite time bounds to get an all-time bound for all time from time 0. So I have a bound from some n0 onwards, and these other works give a bound for some n0, let's say. So you just stitch them together, and one can get a bound forever. So that basically uses concentration inequalities for martingales. And I had some work long back, but then there was an improvement by one of my PhD students called Samir Kamal, so I had to assume a stronger condition on the martingale differences. He weakened that significantly and got a better bound. And then more recently, there's a paper with another PhD student, Gugan Tope, who actually gets a stronger bound, but we use this Alexiev's nonlinear variation of constants formula. It's something worth knowing. For some reason, not too many people seem to know it. For that, we need continuous differentiability of H. So whereas Samir Kamal's bound could work with Lipschitz H. So these are the kind of things which I have been involved in. And yeah, as I said, you can stitch them with the finite time sample complexity bound to get an all-time bound.
So the last sort of thing that I had was more like in terms of usage of samples.
Yeah.
So I mean the field also seems to have again, I guess part of RL is there seems to be an infinite variety of what you can do, and so some models, and I know you have had prior work here with Dilip where you sort of construct the model first. So you take all your random samples initially, you construct the model and you iterate the random operator. Or you use the stochastic approximation method where you sort of get a sample at a time or a finite number of samples at a time. And which of these seem to be better? And sometimes in simulations, some of the random operators give very fast initial convergence, and obviously they tap out because they're only using a finite number of samples. or then if you switch to the stochastic approximation, you do get convergence, but then you take a long time to converge sometimes, and because you have to the step size decreases slowly. Is there a way to, I mean, you can combine them in empirically, but in terms of analysis, it seems to be very hard to sort of put them together. Are you aware of any
No, I have not
methodology?
thought about it, let's say, but I think it's interesting. Maybe I should look at it, return to these problems again. I've not thought about this, but I guess in terms of practice, it may be problem specific. There's some places the one variety works better than the other, and some other cases there's that I think this is folk theorem, right? The no free lunch theorem.
Yes.
So there's no.
It seems like for random instances, it seems like combining them does very, very well.
Okay.
There's no way to sort of.
Yeah, that's often true actually for many such things. So just to give a just an analogy, okay? Now I'm not saying anything about this particular problem, but for example, these 2 time scale iterations, okay? So one runs some iterations with step size a and some iterations with step size bn, and bn is small O of n. That's the way one does the theory of 2 time scale. You can do the 2 time scale also by doing the slower iteration along the subsample. Okay, so you don't update it every time. You update at tn plus 1, etc., where tn plus 1 minus tn goes to infinity slowly. There's another. And yet another of my former students, Sharaf Bhatnagar, who had done a lot of computational work as well. He told me, and thereafter I have started using it in wherever some computation to do. You combine the two, it works better than either of them. So you sort of do along the subsample, maybe a fixed window, say every 100 sample or something, don't have to increase it. Slowly decreasing step size, but along the subsample, it works better than either pure slowly decreasing step size or pure increasing windows. That's an interesting thing. This is a kind of practical tweak which seems to do well. So I think in general, it seems probably one should have some kind of a rule of thumb that you combine the two diverse ideas often does better than either.
Sure. Yeah, I know, but it seems like analysis is hard to come by for those type of things.
Yeah, I think it's
the last sort of thing about usage of samples in some ways is since so you said like in most of the Watkins methodology, and there's this other train of RL thought where you basically have a sample trajectory that is a sample using some policy. The assumption is this policy samples well. And then you sort of build your learning on top of that. And in some sense, your performance is also governed by the mixing time of that policy.
Yeah.
But is there a way, I mean, are there schemes that look at, that can adapt the sampling policies? So you have the sample, you have it run for a certain phase. You don't know whether it's mixed or not, but you know that, say you visited all the state, I mean, or if you may not have visited all the state action pairs, but you form an estimate of the Q function, and you get a candidate optimal policy. Obviously, you're not there, but then you combine that with the original sampling policy, and then sample on this new policy, and then sort of do these in phases. Are there schemes of that kind? Is there any analysis of those schemes?
Often I can't think of it in the Q-learning context. So there has been some analysis of slowly decreasing step sizes long back. I think it was this Singh. I forget the 3 authors. Singh and Zepeswari are 2. I forget who the 3rd one is. And they use kind of the softmax kind of thing and slowly peak it. So perhaps the offer does not adapt to it in the sense that the epsilon in decrease slowly doesn't depend on the history. Now, there's another similar work I have seen is in the bandit bandit setup by Virat Shah, Jose Blanchett, and Ramesh Johari, where they have something called balanced exploration. So they basically wait for a certain length of time till every arm has been sampled up to a certain number of times which they specify. Thereafter, this kind of free for all. So it looks like a basic idea which can generalize, can extend to reinforcement learning as well. And again, I guess it's a thing worth exploring. But I'm not, see, I'm not on top of the entire RL literature, as you admit that. Particularly being an E guy, I tend to look more at my control compatriots rather than I don't dig deep into the CS literature. So I might have missed much of this. It's quite likely.
No, thank you. So any other questions? So I think I gave my perspective and questions. So I'll let the floor open for other people to ask questions.
I have a question not exactly related to what the theme of the talk, but along the lines of what Vijay is mentioning in about the convergence guarantees of Q-learning with stochastic approximation when you are using actually function approximation, like large scale state space. So I know that there are impossibility results for cases, etc. But recently, probably I think you are familiar with this work. I think I have seen you in one of this online talk by Shyam Kakade and his group on showing the convergence of policy gradient approach with function approximation. So earlier, like 4 years back, I thought that the convergence was limited to local optima, but now they seem to rigorously show that you can actually have global convergence under like mild enough conditions. So, but that's kind of pure gradient descent approach without using the theory of stochastic approximation. And later, in a later work also includes some kind of exploration. So is there an analogy for Q-learning with function approximation with provable guarantees to optimal?
Not that I know of, but actually yesterday I attended a talk. It was a kind of late, see, because I am in India, most of these talks are late at night, and today I'm okay. I sort of took a nap ahead of time to be fully awake. But so I didn't latch on to all the details of it. It was by a guy called, I think, something Agassiz, and he referred to some work by Francis Bach and Chizat. And there they seem to have so basically the problem is that the nonlinearity, because for linear, the policy violation case you can prove convergence. So just by scaling the right hand side, the part of the right hand side appropriately, they sort of make it look like something going along the flattened manifold. So the tangent space movement along tangent space is almost linear. And that seems to get them a convergence. I have to read this properly. This is something I came to know yesterday. So there's some papers by, I think, the first one is 2018 by Chizat and Bach, and second one is Chizat, Bach and Ulayan or something, some third one, which is 2020. So it's fairly recent.
Thank you.
So any other questions by anyone else?
I have one, if I may. Can you hear me?
Hello, Samir? Yeah, we can. Please go ahead.
First, Vivek, I am sorry that I had to join your seminar a little bit late. I had to take care of a certain thing, and it prevented me starting joining on time. Sorry. Second, thanks for interesting seminar, and Vijay, thank you for very interesting questions. It's a lot to what I heard and all. But the question that I want to ask you, Vivek, is the following. So you have a statement that the algorithm that you consider is converging to the set of equilibria, which are minima or maxima, whatever you're looking for your. Now, of course, I'm sure that you and everyone else will be interested to converge to global extremum rather than to the set of extrema in general. So did you try to modify your search so that indeed will be some just guarantee of converging to the global extremes?
So our intention was to analyze what happens because of this nonlinearity. You'll have to change the algorithm in a non-trivial manner. So I think this paper by, one of the papers by Yun Shen, I don't recall the details, but one of the papers by Yun Shen actually non-trivially modifies the algorithm to make it converge. So I think that's certainly, that's the direct, if you want convergence to a unique point, you have to change the algorithm. But what we looked at is what happens to the algorithm as is if you introduce the behavioral aspect to it.
Now, what I had in mind is the following. Not
Hello, I'm losing your voice.
Yeah,
okay.
we cannot. Yeah,
Okay.
yeah.
With that, I have microphone practically in my mouth. Is it better? Not really.
Not very.
We still have a lot of
Yeah.
distortion. Yeah.
I tell things slowly. Let us consider
Yeah.
a stochastic approximation algorithm
Yeah.
where the initial point
Yeah. Hello, I think I heard up to initial point and then I lost again.
Yeah, Samian, we are not able to hear the whole thing carefully.
So what I'm saying is initial point.
Yeah.
Let's assume uniform. You can hear me, guys?
Yeah.
With some distortion, yeah.
Now, so select this initial point and converge to an equilibrium. And after that, restructure this initial distribution of initial points so that the probability of selecting or converging to this initial point, selecting this initial point close to this extreme to converge becomes larger. So you add a little bit delta part of probability around this point. And how much you add, it depends upon how good, how deep this minimum, for example, is. Now you have another distribution of initial points. And you continue going like that. In this case, it's possible to prove that in the limit, your initial distribution of initial point is a delta function in the global extremum.
Okay. So it becomes, yeah, so it's somewhat like simulated annealing. That the original version by Cherny of simulated annealing was like that. You run a Markov chain, then you decrease temperature, run it again, and so on. So I guess, yeah, I guess one can make. So this incidentally, there's also, so this is not a gradient system, but there's also analysis of simulated annealing algorithms where it's not a gradient system by Laurent Miclot in Toulouse. So which shows that if you slowly decrease the noise, it concentrates on the minimum of the Friedlin-Wenzel potential. So I guess one use those ideas here. That's an interesting direction also.
See, it does not have to be a gradient.
Yeah, that's what I'm saying. But there are extensions to the non-gradient schemes by Laurent Miclot. So if you have a stochastic differential equation with slowly decreasing noise, then the distribution will concentrate on the minimum of the Friedlin-Wenzel potential. That's the rate function in the small noise limit results of Friedlin and Wenzel.
Yeah.
Okay, so thank you.
Any other questions by anyone? If not, let's thank Vivek for a stimulating talk, and there were a lot of questions after that as well. So Vivek, we were supposed to meet in 15 minutes, but whenever you're ready, you can let me know. I can be on, like, come on like
Okay.
that. Yeah. You
So
can have a short.
Also, I basically have to have a quick dinner. That's all.
Yeah. So that's what. Whenever you finish, let me know.
It's all set up for me already.
Yeah. Okay. All right. Thank you. I'll talk to you soon. Yeah.
Okay.